the theory of this interference fringes formed due to Fresnel Bi-prism is same as the theory of Young's double slit experiment. Okay, so suppose the distance between these two sources, virtual images S1 and S2, is D. Okay, and the distance between this slit and the screen is capital D. Okay, so we can write separation between virtual images S1 S2 is equal to D, and separation between virtual images S1 S2 and screen XY is capital D, which is same as the Young's double slit experiment. Now, if the wavelength of the monochromatic light source S, which we have used, is lambda, then the fringe width will have the same expression as the Young's double slit experiment. So, fringe width is given by beta equals to lambda d by d. Okay. Now, if the distance between the source and the biprism is x, and then the distance between the biprism and the screen is y, then capital D is x plus y. So we can replace it as lambda into x plus y divided by d. Okay. Now, what we can do to obtain the sustained interference fringes on the screen, what we need to do, sometimes we have to adjust the distance between the source and the biprism, so that a sustained and good interference fringes are formed on the screen. Okay, so to now find the proper distance between, so as we change this portion, change the distance, okay, of the biprism or the position of the placement of the biprism, the separation between the virtual images will change. Okay, so now to find, so what should be the proper separation between the virtual images S1 and S2? Okay, so now let us find that will depend on this refracting angle of this biprism. So suppose this refracting angle of the biprism is alpha, and this is, as these two are identical prisms, so this angle is also suppose alpha. Okay. Now suppose, so now we'll find the determination of distance between two virtual sources. So distance between two virtual sources. Okay, so we know, if you know the properties of prism, if the refractive index of the material of the prism is mu, suppose refractive index of material of the prism is mu, then here at first let us draw the angle of deviation. So this ray should have gone along this line, but now it has deviated in this direction, okay, towards E. So this should have been the straight path of the ray without any deviation, but now it has suppose deviated by this angle, which is suppose phi. Similarly, this ray should have gone along this direction, but it has deviated by some angle, the same angle phi. Okay, so if this angle is phi, this angle is also phi. Okay, and this angle is also phi. Okay, so now if refractive index of the material of the prism is mu, then we know by properties of prism, angle of deviation, we know there lies a relation between angle of deviation and the refractive index and the refractive angle. Okay, angle of refraction alpha. So which is phi equals to mu minus 1 into alpha. So angle of deviation phi is equals to mu minus 1 into alpha, where mu is the refractive index of the material of the prism and an alpha is the angle of refraction of the prism. Okay. Now, as you know that we have assumed that the distance between the source, okay, and the prism ABC is x. Okay. Then from the figure above we can say that, now you see this S1 is equals to half of d, which is d by 2, and S2 is also half of d, which is d by 2. Okay, so from this angle, you see this right angle triangle. So this is the right angle triangle. So here you see, and if you consider this much distance to be x, because it is a very thin, the Fresnel Bi-prism is very thin. So this much distance, we can say this almost equal to x. Okay. So this much distance or this much distance is almost equal to x. So from this angle, triangle, you can see that, so this is the hypotenuse, this is the right angle, and this is the base, and this angle is phi. Okay, so if we take the perpendicular by base is equal to tan phi. So tan phi is equal to S1 divided by x from this prism, this triangle. Again for this triangle, this angle is 90 degree. This is the base, this is perpendicular, and this is the hypotenuse, and this angle is phi. So for this triangle also, tan phi is equal to normal by base, which is SS2 divided by x. Okay, so we can say that. Now so if we name them, suppose if we name them as, suppose this point is M and this point is N. So for this triangle S1 M, so now for triangle S1 M, this is a right angle triangle, right angle triangle. So S1 divided by x is, if I write S1 M is equal to tan phi, which means that S1 divided by S1 M is x equals to tan phi, or S1 is equal to x into tan phi. Similarly, for the lower triangle, which is S2 N, okay, so we can write for right angle triangle S2 N, S2 divided by, so S2 divided by S2N is again tan phi, divided by S2N is equal to tan phi, or SS2, now S2N is x equal to tan phi, or SS2 equals to x tan phi. Okay, now if we add this SS1 and SS2, so we can say that SS1 is equal to SS2 is equal to x tan phi, almost equal to x phi, because phi is very small. Because the angle of refraction alpha is very small, then the angle of deviation will also be very small. Okay. So therefore, what is the separation between the two sources, two virtual images? So separation between the two virtual images is S1 plus SS2, which is equal to D, which is 2x phi. Okay. Now we know phi is equal to mu minus 1 into alpha. Therefore, D is equal to 2x mu minus 1 into alpha. So this is the separation between the two virtual images formed by the Fresnel Bi-prism experiment.